some of the things that we're looking at and doing in the context of MPI to help scaling, to help to be able to scale communication support to extreme scale. So I'll talk about, first of all, what the challenges are in terms of a communication library, and specifically MPI. Of course, the focus on MPI is obvious because MPI is a ubiquitous communication protocol that applications use. And then I'll talk about some very specific items that we've started to look at and are starting to move into the InfiniBand standard to try and address some of these issues and really try and set up InfiniBand to be the scalable infrastructure it needs to be able to help to accommodate communications at extreme scale. And so briefly, one can spend a long time talking about issues around scalability of MPI and the like, but I chose several items here that are obvious, that are really real challenges in terms of communication for large-scale applications. And so first of all, just scalability of the communication infrastructure. And so there are aspects here, both of in terms of point-to-point communication, as well as in terms of collective communication. So both pose a challenge when you're trying to reach jobs that have on the order of 1 million endpoints or more. Both pose a challenge in terms of infrastructure for supporting such communication in an effective way. And so I'll talk a bit about some of the things we're starting to do along those lines to improve scalability. The other thing, of course, one wants to do as the size of the problem increases and as the portion of communication, as communication becomes a larger and larger portion of overall communication, if one has to go to very, very small computational work quanta, the ability to really overlap communication and computation becomes more and more important to be able to scale applications and be able to take full advantage of the capabilities that systems provide. And so that's yet another challenge. And of course, the well-documented issues around system noise, which are very much coupled to the collective operations. Minimizing the amount of unnecessary data motion, or I should say minimizing data motion. And again, one of the challenges, there are several issues associated there. One, just not try and get the CPU out of the way, so the CPU doesn't have to be involved in data motion all the time. And the other, of course, is reducing the memory consumption. Energy consumption. So if you can reduce number of memory copies, you can start impacting some of the things that are considered to be very expensive from an energy perspective. And of course, there are issues around easing access to the network. So that sort of puts a frame of reference around the sort of problems that we're trying to deal with in terms of scalability. And so the first thing I want to talk about is a new transport mechanism, scalable transport mechanism called a dynamic and connected transport that's really aimed to start as a first real shot at addressing scalability issues within the InfiniBand spec. With IB spec, as people are aware of it today, there are two transports that are widely in use. You have the reliably connected transport that's considered a very high performance transport. Provides support for RDMA operations as well as atomic operations. Bandwidths are high and latencies are low, but of course there's a scalability limitation in the sense that with RC you have to dedicate a connection for every pair of communicating processes. And so of course you can play games about how you do that. What a lot of communication libraries do is just open static connections and have those live on, or you can do something a little more clever but also more difficult to, more resource intensive and time consuming, as you can dynamically manage some sort of cache. On the other hand, you have the UD transport, or the unreliable datagram transport mechanism, which is extremely scalable. You can use a single QP per endpoint and communicate with all endpoints simultaneously. But it has the limitations in terms of the sort of communications that it supports. So it doesn't support RDMA. It's not a reliable transport, obviously, by the name. It doesn't support atomic operations and the like. So it's very scalable, but not as performant as one would want. So obviously, a natural conclusion, a natural tendency there would be to look for something in between, to try and come up with a solution in between that provides both high scalability and high performance. And that's really, yes?
Conspicuous by its absence is reliable datagram.
Because most hardware doesn't support it.
Why not? That's the problem. Why wouldn't you just support it?
Because there's an alternative way to support it.
Okay.
Yeah, I mean, there are issues in terms of resource sharing and the like with reliable datagrams. Yeah. I mean, yeah. So DC is actually, it's not a reliable datagram, but it has characteristics of it. And so, what DC is really, as I alluded to before, it's this combination between a single communication endpoint that can communicate to everyone and all other endpoints, and simultaneously support a reliable protocol. And so you can also do on top of it RDMA, as well as atomic operations. And, just to remind people in terms of where we are today with the scalability of existing. Well, all of this is existing actually, but previously existing communication protocols in terms of endpoint resource consumption, and really focusing here on the number of queue pairs that need to be opened. Won't go into a lot of detail here, but for RC, it's clear that the total number of queue pairs necessary in a system, it basically scales as the number of endpoints squared. So a given endpoint, a given endpoint will need to support, if it communicates with everyone, will need to, in this model, needs to somehow support something that scales linearly with a number of processes in the system. So that's obviously expensive, as everyone knows. I mean, this is one of the challenges, has been one of the challenges in terms of resource scalability for communication libraries using InfiniBand. Of course, there's XRC, which shares the resources between endpoints in the same node, but still faces the same scalability problem in the sense that now your scalability doesn't go as the number of processes, it goes as the number of nodes in your system, but still that number, when you get to the number, you're getting to numbers of, or aiming for numbers on the order of 1 million plus, on the order of 1 million nodes. Of course, you have a resource consumption problem here. And so reliably connected datagrams are mentioned here. But in terms of hardware, they simply aren't implemented. And so from a resource consumption perspective, this is just the resources consumed by the endpoints in a communication library. We can see that as the number of end nodes increases. Sure how as the number of end nodes increases, the footprint of reliably connected transport dramatically increases. XRC, or the shared, improves the situation, but still things are increasing. The resources are increasing linearly with the number of nodes in the system, but then switching to DC, to dynamically connected transport, this is where we start to gain in terms of resources. So the way I think about dynamically connected transport, just to put this up front before I go into a few explanations, a bit of an explanation of what this does is DC is really, as an MPI library implementer, DC is really what I would have done in software in terms of implementing a connection cache, except that it has the advantage that it's done in hardware, and it can do, and so basically what DC does is it sort of sets up a connection cache, but it has the advantage that since it owns the underlying network, it can do a lot of connection establishment speculatively and handle all the issues associated with resources in a very effective manner underneath the covers. And so briefly, the DC transport, a single Q pair can communicate to any other end node in any other end node in the system. So you can take a single end node, single Q pair, and from it send messages to every other node in the system. There's no resource sharing between processes. The resource footprint, as a result, is small. It's fixed, as a matter of fact, and the resource footprint is actually really determined by the communication characteristics of your system. So what this implies here is, for example, so a few things to say here. One thing that does happen with the DC is, since it's a reliable transport, it needs to have a mechanism for maintaining reliability of the data. And so that is, it has to guarantee data delivery. And so what that implies is, the consequence of this is that even though one can send data from a single endpoint to another endpoint, there has to be a mechanism for guaranteeing reliability. And the mechanism for guaranteeing reliability is exactly the same mechanism that's used in RC. And the implication there is that while you can communicate from a single endpoint to every other endpoint, you can't change the context that you're communicating with until the data that's been previously sent has been acknowledged. That is, you have to guarantee reliability. What this means is that while in practice you can send data from a single QP to every other QPs, if you use a single QP and continually change your destinations, you're going to pay that latency penalty associated with the reliability protocol. And the implication there, of course, is that you need to use a number of different sources for the data, or in the language of DC, a number of different initiators. And this is where the hardware capabilities come in. The hardware can only generate a certain number of packets per second. It's just not capable of producing a larger number of packets per second. I mean, it just can't. And that number of packets is determined by communication characteristics of the local node. And so, for example, and so one has to the number of initiators that you need for this is then fixed by that upper number, and that number actually is not very large. So if you think, for example, of a network like ConnectIB that can push packets at around, say, 150, that's not the exact number, but on the order of magnitude of 150 million packets per second. If you assume a round trip, worst case, if you assume a round trip latency of 2 microseconds, for example, for your small packets, which is the toughest one to deal with respect to latency, all that means is you really need to be able to have, at most, 300 initiators, period, to support that communication, regardless of the size of the system. In practice, you actually need a lot of applications need much less than that, because in practice they don't communicate with a lot of endpoints. Although there are definitely examples where that's not the case. MPI all-to-all communication is one of those, but there are ways to deal with this. DC is actually a very good transport to deal with that. Then, of course, communication protocols that don't use, applications that don't use those sort of explicit all-to-all calls, like, SHMEM applications that may use all-to-all communication, but not explicitly. Those, of course, pose a larger challenge. And one does need to actually keep this upper limit number in terms of number of Q pairs. But the point is, the number is small and it's fixed, regardless of the size of the system. And so the memory footprint associated with dynamically connected transport, as a result, is also fixed, regardless of the size of the system. So pictorially, this shows what I've just talked about. So we have here the notion of an initiator, which sends the data, and a target, which receives the data. It's an asymmetric model, very much like XRC. And the initiator sends data you can send data to as many targets as it wants. And just remind people that, again, since this is a reliable protocol, there's a latency impact associated with this when you change your targets. You have to make sure that the reliability context is maintained. And so if you think about current, what happened here? With RC today, of course, if you're going to establish connections between all endpoints, the connection map is very dense. But if you go to dynamically connected transport, what happens is your connections are sparse. I mean, they depend on your communication pattern of your application, and the application doesn't have to do anything. The hardware is the one that manages all this based on the current state of communication. It doesn't. There's no speculation here, nothing like that. It simply handles communication as it comes by and dynamically changes the connections, reuses connections. The next thing I'll talk about briefly are the cross-channel synchronizations, which our implementation of this at Mellanox is as core direct. Those of you that have heard me talk at HPC Council talks in the past have seen part of these slides. But the implication here is that the support for these cross-channel synchronizations is going upstream into the main OFID source code base for wider use. And so, just to remind people what cross-synchronization is all about, is it really provides what it adds to the IB spec is definitions are mechanisms for synchronizing activity between separate Q pairs. And so what this implies is that one can create lists of activities that involve synchronization between different Q pairs on the same node, and feed those to the net to give those to the HCA. And if your HCA, for example, offloads communication to the network, you've basically offloaded a whole sequence of operations to the network to let the network manage them without needing CPU intervention. And this is really one of the goals of this technology. One of the things that this also lets you do is take advantage of once you get to these sort of synchronizations, you can start to build support, or we have built support for collective communication, for example. And you can go the further step of taking advantages then of hierarchies within the network and build even more efficient communication to support in the network. So I've mentioned, Brian, what's my time frame? 8 minutes, okay. So I'll rush through this. As I said, this technology is aimed specifically at supporting collective communications, which is really one of the most challenging problems from a scalability perspective for applications and communication libraries. This is often the factor that determines overall scalability of collective of parallel applications at large scale. Collective communications, of course, are also the main source, or often the main source of the negative impacts of system noise at large scale systems. And so this technology is really, this capability is really aimed at providing the hooks that one needs to be able to start dealing effectively with this scalability challenge. So a cartoon that probably several of you have seen in the past, talking about the impact of system noise. So collective in high performance collective communication algorithms, they're always coupling between all ranks in the given group, or in MPI language, in the communicator that's involved in the communication, whether it's implicit or explicit. When the system needs to provide services, service I/O, service whatever else it does, of course it takes away time from the application, and so collective communications is negatively impacted by that. If you take the next step and once you set up the sequence of events, you put it to the network, system activity no longer impacts the collective operation, and so you've immediately dealt at most stages of the collective operation with the negative impacts of system activity, the negative impacts on the scalability of the application. The system still always has to provide its services for other reasons. And then, of course, you can really take advantage of this if you go and start using non-blocking collective communication, because what you can do is you can set up your collective communication, hand it off to the network, go off and continue computation, and when you need the results, check and see if they're there. So now that non-blocking collective communication is part of the MPI standard, MPI libraries are starting to support this communication. It gives the application the ability to start and really look at change the way it takes advantage of network resources to improve its scalability. Let me briefly mention here, as I said, the key features in the cross-channel communication is the definition of synchronization primitives that lets one synchronize activity between completely unrelated queue pairs. There are primitives that let one basically wait until a certain number of operations have completed relative to a completion queue in a completion queue, or it can explicitly enable operations in other send queues. So there are two mechanisms for doing this. What that one does to take advantage of this is sets up the list of operations that need to be executed, that one wants to execute in parallel. You do that on every endpoint, submit them to the post the task to the queue pair, and let the HCA continue and progress. And as I said, if your HCA handles everything in the network, what this ends up doing is it ends up moving all communication management to the network. So not only do you have the asynchronous RDMA type of operations, but you also have asynchronous management of communication. So I will skip a lot of the details now because of shortness of time. I'll just mention here pictorially. Again, this is what I just mentioned now. At each node, one sets up a list of operations, post those operations to the completion queue, and waits for completion. So a simple example here of barrier recursive doubling algorithm, very, very simple, four processes or 4 endpoints participating in the exchange. You can give it a list of operations that I show here. You know, for rank this is actually for rank 1, not rank 0 the way it says here. Basically, you have your first data send. Remind you, we have process 1 will send first to 2. Then the next set it will send to 3. It will wait until it receives data from 2, and then it will send to 3. And so this is exactly reflected in the task list here. So we have basically a master queue pair that manages when other QPs are allowed to send data through this, as I mentioned before, through this enabling these operations that are already posted, making them visible to the hardware, or you can explicitly just use 2 queue pairs and build your completion. Will build in the appropriate completions and post events and post them to the queue. And again, at the end, you have from a completion perspective, you wait on only a single completion versus 4 completions if you were going to wait for everything on a per task basis. This is nothing new that's being added to the standard, by the way. This already exists. This capability has existed for a long time in the hardware. So briefly, in the very 2 minutes I have left, I mentioned very briefly the handling of non-contiguous memory. So again, one of the things, at least from a communication library's perspective, is very difficult to deal with, just in the sense of the amount of resources that one uses, is dealing with non-contiguous memory. And so most folks know that most applications writers probably, well, you know what you do, is a lot of times what happens, because of the lack of support for non-contiguous memory handling by the hardware, what often happens is applications, before they hand off a chunk of communication to the library, will basically do a local copy of the data into some temporary buffer, and then hand that to the communication library and let that happen. And so what we've done in ConnectIB is add explicit capability to handle non-contiguous memory to the hardware. Now the capability existed before in the context of scatter-gather lists, but scatter-gather lists are very inefficient. If you have anything periodic, they don't handle periodicity well at all. And in terms of the amount of memory you need to manage those memory transactions, also scatter-gather lists tend to be inefficient, unless, of course, each entry there represents a large amount of data. And so the ability here is really to add, the new feature here is really to be able to add a much richer set of capabilities to describe non-contiguous memory. The HCA itself manages the non-contiguity. That is, the applications don't have to pass in a contiguous region of memory, and the HCA itself will do the gather on the gather and the scatter, actually in a single transaction, between 2 endpoints on its own. So there are two new ways that are being added to the IB spec to support this. One is the ability to start to describe regions of memory that are separate regions of memory. Start with separate regions of memory and combine them into a single memory key that describes the region that, from the hardware's perspective, the hardware will treat it as a contiguous region of memory. You still address these at the application level. The addressing is still handled in terms of the virtual address, virtual memory addressing, or physical memory addressing, for that matter, if this is done within the kernel of the original
the user of the library, the user of the service, but what the hardware will do will treat these three regions here in this example as one contiguous region. So you can give it a pointer, they say start in here, which would map here to the memory key, tell it take the next, say n number of bytes, and if that n number of bytes passes this boundary here, the hardware just treats it as contiguous. So the user doesn't have to do any sort of copying of these memories into some sort of contiguous region of memory from its perspective, and create a region of memory that's contiguous in its virtual memory to be able to take advantage of this capability. And of course, the other advantage of this thing is, since this is described by memory keys, you can do it both in the source and the destination. And so you can do scatter-gather of this data. And so you can even do an RDMA to a region that's non-contiguous at the target. And so the next the other capability that's been added is the ability to have a much more compact representation for data that has regular structure to it. So with scatter-gather lists, what you needed to do is, this should have been colored here. This is a non-contiguous region of memory going down the columns. If you were using a scatter-gather list the way you you have been able for quite a while, this would require 8 entries in the scatter-gather list. And if each of these, for example, is a double, of course, this is a very, very inefficient way of describing the memory. With a new definition, a single entry describes this. And so it's effective, it's efficient on the host side of things. It's also efficient on the HCA side of things, in that the gathering of the data, or the scattering of the data, of course, depending on if you're a source or destination of the data, all is handled by the hardware. The hardware adds another nice capability, is that you can take regions that are separate regions and interleave them in this memory key. And so no memory copy is required here. You just describe a memory key that basically combines these two, and so you can get very, very fancy in the way you want to handle in the sort of memory layouts that you want to describe, that you want to hand off to the hardware. So that's all I have.